what we're about to do is find a way to think about sine and cosine where we can sort of free ourselves from necessarily having to think about triangles. So what we're going to talk about here is, well, let's just cook this up. So let's ask the question, what if the hypotenuse for our triangle was 1? Now, why am I asking such a question? Why would it make sense to say, well, what if the hypotenuse is 1? Think about it. All of the 6 ratios that are related to our trigonometry could be built up from sine and cosine. And while sine and cosine both have hypotenuse in the denominator, it's always nicer to deal with things that aren't fractions instead of fractions. So if you didn't want to deal with fractions related to sine and cosine, you could just let hypotenuse be 1, and then you wouldn't have to deal with fractions there. There being sine and cosine, the two trig ratios that give you access to all 6. So if we let hypotenuse be 1, we could have an easier time of making sense of sine and cosine, because sine would just be opposite and cosine would just be adjacent. So what if we did let the hypotenuse be 1? Well, say, as I drew this triangle here, say the position horizontally here is x, and the vertical movement of the triangle is y. Well, what you can see here, looking at this, if you pick the angle, I'll use t again because the book likes it. Say the angle is t here. Well, the sine, note here, the sine of your angle t, sine always opposite over hypotenuse, is just y over 1, or y. I tell you what, I'll write y over 1. Why not? Cosine t, adjacent over hypotenuse, x over 1. And having written what I have here, of course, anything divided by 1 is itself. So let's just call it what it is, y of x. This was the virtue of choosing hypotenuse equal 1. But check this out. I'm going to take this picture that we've got here, and I'm going to make it more meaningful. I'm going to take this triangle, and instead of just viewing it ambiently on the board, let me imagine that this triangle has been based at the origin of the xy plane. Totally reasonable thing to do. I mean, you could do that. You could set the triangle down in the xy plane. And now what you could notice is, once you do this, because I happen to have picked a triangle with angle t out here, but of course, if t was slightly bigger, I just have a point up here where my triangle would be drawn. If t was even bigger still and the angle was more open, a length 1 line in that angle would be somewhere up there. If t happened to be smaller in angle, well, as long as my hypotenuse is 1, which is what we're thinking in terms of here, I would just have a segment of length 1 from the origin that would be down here. If t was even smaller still, you'd have a segment that would go out to there. You could build a triangle from any of those points. In fact, if you looked at all points where you could draw triangles from in this orientation, you would have all points along a part of a circle, would you not? Because all of these points are 1 unit away from the origin. It's essentially like using a compass at length 1 and drawing an arc there. Noting that every one of these points which is on the unit circle is of the form x comma y, because every point in the plane is of the form x comma y. But in particular, since the x comma y's are on our circle, since the x comma y's are corresponding to triangles with hypotenuse of length 1, x is really more than just x. We've already showed that x is equal to the cosine of our angle t. And y is more than just y. While it is the vertical position, yes, the vertical position is the side opposite to our angle t. And since the hypotenuse is at measure 1, the sine of our angle t, y over 1, simplifies to just y. So our y value is really just the sine value for our angle. But now, look what we've done. We've taken our triangle, drawn in this orientation, and given us a quarter of a circle of possibilities. What if we just extend that? And instead of saying we're only going to look at angles between 0 and 90, what if we say we're going to look at angles of any degree measure? Well, if you do that, you would get a circle of radius 1 extending all the way around. So what we can do here is we can extend the circle all the way around. And this is to consider angles beyond 90 degrees. I mean, the 90 degree, the possibilities for the angle in the triangle, if we draw the triangle in the traditional sense, is only between 0 and 90, which would only give us that first quadrant. But if we open up our mind and say, well, hey, we got a circle here, let's just extend this quarter of a circle all the way around, well, then that could give us a way to find sine and cosine values for any angle, even angles beyond 90 degrees. For the angles that are between 0 and 90, the notion corresponds exactly to our case of triangles, but even beyond 90 degrees, you could then have a notion of sine and cosine. So when you use this circle to look at the sine and cosine values, this circle of radius 1 centered at the origin, you get the sine and cosine values for all the triangles that you could draw. You also get sine and cosine values for triangles that you can't even draw. By the way, this circle goes by a name. This circle is called the unit circle. Now, why is it called a unit circle? It's called a unit circle because its radius is 1 unit in length. Why is it called the unit circle? Because, of course, there are infinitely many circles of radius 1 if you move this thing around the plane. It's called the unit circle because it's centered at the origin. So when we talk about the unit circle, it's radius 1 centered at the origin. It's the circle that we're talking about here. And the unit circle has the curious relationship that every point on it is of the form cosine cosine.